In 2008, my graduate student Yasuhiro Sakino and I proved something that sounds impossible. There's a fundamental speed limit in nature for how fast information can be scrambled. Not the speed of light, something completely different. We showed that black holes scramble information at the absolute fastest rate physically possible. Drop something in, and within a time that scales logarithmically with the black hole's entropy, the information is completely mixed across the entire horizon. Nothing in the universe can scramble faster. And that speed limit, it's the key to understanding how black holes process quantum information without destroying it. Look, let me tell you how this started. It was around 2007, and I'd been obsessed with the black hole information paradox for almost 15 years by that point. Patrick Hayden and John Preskill had just published this incredible result. They proved that if you want to recover information from Hawking radiation, actually decode what fell into the black hole, you'd need to wait until more than half the black hole had evaporated. Then you'd need to perform this exponentially complex quantum computation on all the radiation you've collected. When I read their paper, my first reaction was, that's impossible. Not mathematically impossible, they'd proven it rigorously, but practically impossible. The computation they were describing would require manipulating something like 1070 qubits simultaneously for a solar mass black hole. No computer in the universe could do that. But then I started thinking, wait a minute, the black hole itself is doing that computation. It has to be. The black hole is taking the information about what fell in and spreading it across the Hawking radiation in this incredibly complex way. So the black hole must be performing this exponentially hard computation naturally, just as part of its evolution. That's when Yasuhiro came into my office. Yasuhiro Sakino was one of my graduate students at the time. Brilliant kid, incredibly technically sharp. He'd been thinking about related problems in ADS-CFT, and we started talking about this question, how fast can a physical system scramble information? I remember the conversation clearly. I said, Yasuhiro, there has to be a limit. Information can't spread faster than light, so scrambling can't be instantaneous. But what's the actual time scale? He looked at me and said, well, if there's a limit, black holes must saturate it. They're the most extreme objects in nature. That insight, that black holes should be the fastest possible scramblers, that became our conjecture. We decided to prove it, all right? So let me explain what we mean by scrambling and why it matters. Think of information like this. You drop a book into a black hole. That book contains information, the arrangement of words on pages, the specific molecules in the paper, the quantum state of every atom. In principle, quantum mechanics says that information can never be destroyed. It has to go somewhere. Stephen Hawking's calculation in the 1970s said the information just vanishes. I spent 28 years arguing he was wrong about that. By 2008, most physicists agreed with me. Information must be preserved, but although it's preserved was still a mystery. Here's the current picture. The black hole emits Hawking radiation, thermal particles that leak out over billions of years. Eventually, the black hole completely evaporates, and all that's left is this cloud of radiation. The information about the book must be encoded in that radiation somehow. It can't be lost. But here's the problem. The early radiation that comes out looks completely random. It's thermal. It's like the radiation from a hot oven, no structure, no information, just heat. How can the information about the book be encoded in that? Patrick and John's answer was it's encoded, but in this incredibly subtle way. You have to collect more than half the total radiation, then perform this exponentially complex quantum computation to decode it. The information is there, but it's maximally scrambled, spread out across all the radiation in the most complex possible way. Now, here's where the timescale question comes in. Let's say you drop the book into the black hole at time 0. How long does it take for the black hole to scramble that information and start encoding it into the Hawking radiation? It can't be instantaneous. Information spreads at the speed of light, so there's got to be some delay. But it also can't take forever. The black hole is already radiating, so the scrambling has to happen fast enough that the outgoing radiation can carry the information. Yasuhiro and I wanted to figure out what's the minimum possible scrambling time. And do black holes actually achieve that minimum? Here's why this matters. If scrambling is too slow, then the early Hawking radiation leaves the black hole before the information gets scrambled into it. That radiation would be completely independent of what fell in. The information would be stuck inside, and when the black hole evaporates, information is destroyed. Paradox. But if scrambling is fast enough, if the black hole can mix the information across its entire horizon quickly, then the information can get into the early radiation. The paradox is resolved. So the scrambling timescale isn't just some technical detail. It's central to whether black holes destroy information or not. Now, there's another piece to this puzzle. In quantum mechanics, there's a fundamental relationship between time and energy given by Heisenberg's uncertainty principle. If you want to scramble information on a timescale t, you need energy fluctuations of order 1. The faster you want to scramble, the more energy you need. For a black hole, the relevant energy scale is its temperature, which goes like 1 m, where m is the mass. Big black holes are cold, small black holes are hot. But in all cases, there's this fundamental trade-off between how fast you can scramble and how much energy you have to work with. Put it all together, and there should be a minimum scrambling time that depends on how much stuff the black hole has to scramble. It's entropy. We wanted to figure out what that minimum is, so Yasuhiro and I started working on this problem together. The first thing we did was think about simpler systems. Forget black holes for a second. What's the fastest a generic quantum system can scramble? Here's the setup. You've got a quantum system with some large number of degrees of freedom. Think of it like n qubits, where n is huge. You start in some simple, unscrambled state, then you let the system evolve under its natural dynamics. The question is, how long does it take for a simple initial perturbation to get completely mixed across all n degrees of freedom? There's a beautiful way to measure scrambling mathematically using something called out-of-time order correlators, or OTOXs. I won't go into the technical details, but basically, you look at how operators that started at different times and different locations in your system start to overlap and interfere with each other. When the OTA decays to 0, your system is fully scrambled. For most systems, like a box of gas or a crystal lattice, scrambling is pretty slow. It takes a time proportional to n, the number of degrees of freedom. Information spreads diffusively, like heat spreading through a material. One particle bumps into another, which bumps into another, and so on. It takes many, many collisions to mix everything up. But black holes are different. Black holes have this enormous entropy. For a solar mass black hole, the entropy is something like 1077 in fundamental units. That's the number of quantum states the black hole can be in. If scrambling time scaled linearly with entropy, it would take far for a black hole to scramble. But we realize that can't be right. Black holes are strongly interacting systems. Every part of the horizon is gravitationally coupled to every other part. It's not like a gas where particles only interact when they happen to collide. In a black hole, everything is interacting with everything else all the time. We conjectured that for a maximally chaotic system, a system where the dynamics are as strongly interacting and nonlinear as possible, the scrambling time should scale like the logarithm of the entropy, not linear logarithm. That's a huge difference. For a black hole with entropy 1077, linear scaling would give you a scrambling time of 1077. Logarithmic scaling gives you something like log 1077 d177, vastly faster. Now, why logarithmic? Here's the intuition. In a strongly chaotic system, information spreads exponentially. Think of it like a branching tree. You start with one qubit that's been perturbed. After one time step, that perturbation has spread to 2 qubits. After 2 time steps, it's spread to 4. After 3 to 8, it's doubling at every step. How long does it take to reach all n qubits? Well, 2d to n, which means t-log, logarithmic time. For a black hole, the relevant n is the entropy s, so we conjectured the scrambling time is proportional to log s. But proportional with what constant out front? That's where the temperature comes in. The black hole's temperature T sets the fundamental energy scale. From Heisenberg's uncertainty principle, the minimum time scale for any quantum process at temperature T is 1 dt. So the scrambling time should be something like L² dt to log s. That was our conjecture. We called systems that saturate this bound fast scramblers, and we argued that black holes are the fastest scramblers in nature. Let me be clear about what we proved and what we didn't prove. We didn't prove from first principles that black holes achieve this bound. That would require a complete quantum theory of gravity, which we don't have. What we did prove is that this bound exists, that no physical system can scramble faster than this without violating fundamental principles of quantum mechanics and relativity. We also showed that in certain toy models of black holes, particularly in ADS-CFT, where you can map the black hole to a strongly coupled quantum field theory, the scrambling time does indeed scale like log s. The field theory saturates the bound. Here's why this is so important. For a solar mass black hole, the temperature is absurdly cold, about 10.7 Kelvin. The entropy is about 1077. Plug into our formula, and the scrambling time comes out to something like a millisecond, a millisecond. That means if you drop something into a solar mass black hole within about a millisecond, measured in the black hole's time, not yours, the information about what you dropped is completely scrambled across the entire horizon. Every bit of the horizon knows about every bit of what fell in, and once it's scrambled, it can start leaking out in the Hawking radiation. The early radiation can carry information about what fell in, as long as you're willing to do the exponentially hard computation to decode it. This resolved one of the major puzzles in the information paradox. People had worried that information couldn't get out fast enough. Our fast scrambling result showed it could. Black holes scramble at the absolute physical limit. When Yasuhiro and I first presented this work, the reaction was mixed. Some people got excited immediately, others were skeptical. The skepticism came from the fact that we couldn't prove black holes saturate the bound directly. We were making a conjecture based on analogy with ADS-CFT and arguments about chaos. Some people wanted a more rigorous derivation, but over the next few years a lot of evidence accumulated that we were right. Joan Maldacena and others worked out the scrambling dynamics in ADS-CFT much more carefully. They showed that the dual field theory really does scramble in logarithmic time, and that this corresponds to scrambling inside the black hole. Then Stephen Schenker and Douglas Stanford. Steve was one of my collaborators on the BFSS matrix model back in '97. They introduced these out-of-time order correlators, the OTHAs I mentioned earlier, as a precise way to measure scrambling. They showed that in the SYK model, a toy model for quantum black holes, the scrambling time is exactly logarithmic. That was a huge vindication. The SYK model is solvable. You can calculate things exactly. And it shows fast scrambling, just like we predicted. Since then, fast scrambling has become a central concept in quantum information theory and quantum gravity. People study it in quantum field theory, in condensed matter systems, even in quantum computing. There's now experimental work trying to measure scrambling in real quantum systems in the lab. The connection to quantum computing is particularly interesting to me. It turns out that scrambling is closely related to computational complexity, how hard it is to simulate a quantum system on a classical computer. Systems that scramble fast are hard to simulate. Black holes, being the fastest scramblers, are the hardest things to simulate. This led to my later work with Adam Brown and others on complexity equals action. The idea that the computational complexity of a black hole's quantum state is related to the classical action of spacetime inside the black hole. But that's a story for another time. What I want to emphasize is that fast scrambling wasn't just an isolated result. It connected to so many other ideas. The information paradox, holography, ADAS, CFT, complexity, quantum chaos. It's one of those papers where the implications kept unfolding over the years, and it was a great collaboration. Yasuhiro did a lot of the heavy technical work on the calculations. I brought the big picture intuition about black holes and information. That's what I love about physics. When you work with smart young people who bring fresh perspectives, you can figure out things neither of you could have done alone. So where did this fast scrambling work lead? In a lot of directions, actually. First, it helped solidify the resolution of the information paradox. By showing that black holes scramble fast enough, we closed one of the loopholes that people worried about. The information can get out in the Hawking radiation, at least in principle. Second, it opened up this whole research program on quantum chaos and scrambling. People started asking what OTHR systems are fast scramblers. Can we build fast scramblers in the lab? What does scrambling tell us about thermalization and equilibration in quantum systems? There's been beautiful work on this. Kitov's SYK model, the relationship between scrambling and quantum butterfly effects. Experiments measuring otoques in ion traps and cold atoms. Third, it connected to my later work on computational complexity. Adam Brown and I realized that after a black hole has scrambled, after the entropy has maxed out and the black hole has reached thermal equilibrium, there's still something evolving. The computational complexity of the quantum state keeps growing. Scrambling time is logarithmic in the entropy, but complexity keeps growing for exponential time, something like XPS. That's because even though the state is maximally scrambled, it keeps getting more and more computationally complex. The quantum gates you'd need to prepare that state from a simple initial state keep piling up. This led to the complexity equals action conjecture, which I worked on with Adam and several others. The idea is that the computational complexity of the boundary state in ADS CFT is dual to the action of the Wheeler-DeWitt patch in the bulk. It's a new kind of holographic duality going beyond the usual entropy-based ideas. Fourth, fast scrambling has implications for quantum computing. If you want to build a quantum computer that's maximally powerful, you want it to scramble fast. The faster it scrambles, the faster it can explore Hilbert space and perform complex computations. But there's a limit. Our fast scrambling bound says you can't scramble faster than logarithmic time. That puts a fundamental limit on how fast quantum computers can operate, at least for certain tasks. Black holes saturate that limit. In a sense, black holes are the fastest quantum computers in nature. They're maximally efficient at exploring their quantum state space. And finally, there's the connection to de Sitter space and cosmology, which I've been working on more recently. Our universe has a cosmological horizon, a boundary beyond which we can't see because space is expanding faster than light can travel. Does our cosmological horizon scramble like a black hole horizon? Does it have a finite entropy? If so, what's the scrambling time? These are questions I'm still thinking about, along with Edgar Shagolian, Adil Rahman, and others. The fast scrambling result from 2008 keeps coming up in unexpected places. That's what I love about theoretical physics. You work on a specific problem, you figure something out, and then years later you realize it connects to a dozen other things. After 50 years of doing physics, Here's something I've learned: the most interesting problems are the ones where the answer surprises you. When Yasuhiro and I started working on scrambling, I thought we'd find that black holes scramble in some complicated way that depends on the details of quantum gravity. I didn't expect a universal bound. I didn't expect logarithmic scaling. But that's what the math told us, and once we found it, it made perfect sense. Black holes are maximally chaotic. They're the strongest scramblers in nature. Of course, they saturate the fundamental limit. The universe has these built-in speed limits: the speed of light, the Planck length, the scrambling time. They're not arbitrary. They're fundamental features of how reality works. And black holes, these objects that seem like the ultimate destroyers, the ultimate information eaters, they're actually the ultimate information processors. They scramble at the physical limit. They compute at the physical limit. They're quantum computers on steroids. I'm 86 years old now. Yasuhiro went on to have a great career in Japan working on string theory and cosmology. Every time I see his name on a paper, I think back to those conversations in my Stanford office when we were figuring out how fast chaos can spread. That's the beauty of physics. The problems we solve today become the foundation for the next generation's discoveries. And sometimes a graduate student walks into your office with the right question, and you figure out something that changes how you think about the universe. Next time, I'll tell you about what happens after a black hole has scrambled, when we move from scrambling to complexity. That's when things get really wild.